Hello everyone, I'm Norman Wahlberger and welcome to Algebraic Calculus. In this video we're going to look at vectors, displacement, and center of mass, introducing some fundamental ideas of vectors into planar geometry with connections also to physics. Okay, so one of the very important applications or directions of calculus is to understanding change and the way things change. For a very simple example, suppose that your bank account has $512 in it in January, and in February it has $574. Then in that month there has been a change of $62. That's a kind of change, but it's a relatively simple-minded kind of change. Now in arithmetic or accounting, this kind of change is usually a difference. We're subtracting two numbers to determine how much things have changed by. In calculus, which is motivated more by geometry and physics, change is often a little bit more geometrical or maybe even dynamic. So change is often a displacement measured by a vector. For example, suppose that we're in a one-dimensional situation and we're looking at two particular points, the point 1 and the point 3. Then the relative separation between them, the change that we get from going from this one to this one is, well, we can represent it by this directed arrow whose size is 2. And in fact, we could sort of label this arrow with this little bracket with 2, representing the fact that from here to here, we have to go over 2 units. Now, if this was a physical situation and we actually had a particle moving, then perhaps at 4 p.m. it would be here, and maybe at 12 p.m. it would be here. And then the physicists could talk about how fast it's gone, because there's an element of time as well. Okay? So that's not necessarily intrinsic to the geometry, but it can be quite relevant to the physics. Here is a two-dimensional version of that, where we're moving around in the plane now rather than in a one-dimensional line. So consider the 2 points, one right here and one right here. This is probably the point 1, 1, and this would be the point 3, 2. And suppose that on Monday we have some particle which is here, and on Wednesday we measure it and it's over here. So there's been some change. And that change is measured by this displacement. The displacement now represented by this green arrow or vector, which is now sort of going at an angle. It's not purely in the x direction or purely in the y direction. It has a component of 2 in the x direction and a component of 1 in the y direction. So we could represent this change by this green vector, and we could give it the name 2, 1 with these round brackets to alert us to the fact that this is measuring a kind of a relative separation between 2 points rather than the absolute kind of positional representation that we've seen with points. Okay, so this is the shift that we're talking about, the shift going from absolute positions to relative positions. Talking about how much we've changed going from one place to another place. That's what vectors are all about. So let's talk a little bit more about this one-dimensional situation, which is a little bit simple, and it's not what we're mainly interested in. We're mainly interested in 2 dimensions and higher. But it's useful to think about the one-dimensional case because it's falling into the same pattern, and, well, it provides some important structure for other arguments. Okay, so the one-dimensional line is just a single line, maybe called the number line, 0, 1, 2, 3, 4. Maybe we'll call it x, just to be consistent with what we had before. Now, in this kind of case, a point is represented not by a pair of numbers, of course, but rather by a single number, but still enclosed in square brackets. Okay, so a equals square bracket 1, that represents that point there, while b equals square bracket 4 is that point there. Okay, now, if we're interested in the relative separation between those 2 points, especially as we're thinking about starting from A and moving to B, okay, then the change is represented by this green arrow going from A to B. And we can give a name to this by recording just how far over we've gone, in this case 3, and putting it in round brackets to suggest that this is a relative quantity, not an absolute quantity like the 0.4 or the 0.1. All right, so more generally, an affine point is something that looks like this. A equals x, where x is a rational number and where we have square brackets to remind us that this is a point. Okay, now the relative position of 2 points A and B is a displacement. Okay, the relative positions here is a displacement, not a distance. It might be tempting to describe the relationship by saying that there's a distance of 3 between them, but we don't want to do that. One of the reasons is because distance by convention is always positive, and we want this displacement to possibly be positive or possibly also to be negative, depending on the direction of the change going from A to B. Okay, and we're going to record this geometrically by a vector, just like this. A line segment with an arrow in one end telling us sort of which way we're going. And here's a convention that we're going to be using. So this arrow, we'll write it as AB with a little arrow on top. And to express the relationship, we'll write round brackets 4 minus 1. We'll take the entry here of B and subtract the entry of A. That gives us, of course, 3. And so that's the notation that we're going to use to describe this vector, this displacement between A and B. All right, so that's in the case when A is the 0.1 and B is the 0.4. So we now have the idea of points and the relative separation or displacement between points measured by these new kinds of objects, these vectors that look a lot like points, but they are subtly different, subtly and importantly different. Okay. This kind of vector is enclosed in round brackets. The points are in square brackets. This is a very, very useful distinction to keep in mind and to keep things straight in our own minds. Okay, so we're thinking about these vectors as some kind of directed quantities. They're things with a direction, but also an extent or a quantity, some kind of measurement of how far we're going in that direction. And these things occur in many, many places in geometry and in physics. They're very important concepts. So they include things like displacements that we've already talked about, but also things like velocities, accelerations, moments, momenta, forces, or just general kinds of changes. These are all naturally represented by vectors. So the concept actually has all kinds of different manifestations. The same mathematical concept can work or apply in a lot of different situations. So how are we going to cover all of these? How are we going to officially say what a vector is in such a way that it's general enough and flexible enough to be able to be applied to all these different possible situations? The answer is we're going to try to keep things as simple as possible, all right? To define the objects by thinking about how we specify them. Okay, so here is the actual official definition of, first of all, a one-dimensional vector and then a two-dimensional vector. Okay, so what we've done so far is kind of motivation for this. This is the official legal definition. Okay, so a one-dimensional vector, V, equals A in round brackets, is a rational number in round brackets. That's what a vector is, or more precisely, a one-dimensional vector is. So we don't have to say anything more than that. We just write down a left bracket, then a rational number, and then a right bracket. As long as those brackets are round brackets, then that is necessarily a one-dimensional vector. And we can interpret it in a number of different ways, but what it actually is this expression that we can write down. Similarly, a two-dimensional vector is looking like this. V equals A, B, so a pair of rational numbers. It's a pair of rational numbers in round brackets. Again, the round brackets alerting us to the fact that we have a vector here. So this is our definition of what vectors are. And naturally enough, we could extend this, and eventually we will, to higher dimensional vectors, to three-dimensional vectors, and so on. But to start off with, we'll just think about these one-dimensional and two-dimensional vectors, defined in this very concrete, explicit way. Now, still staying in the one-dimensional situation, how do we introduce these displacement vectors in the context of points on an affine line? Well, if A and B are points, and say A is the point consisting of the number little a, and B is the point consisting of the number little b, then the displacement vector V equals AB. Okay, we define the displacement vector AB is this thing right here. It's the vector whose single number inside is B minus A. We take the coordinate of B, we subtract the coordinate of A, and that is what we put inside here. It's just a single rational number. So that's how we go from a pair of points to a vector. We just take the difference of the entries. But remember that we're starting from A and going to B, so what's inside here is the final entry minus the initial entry. Okay, it's the final entry minus the initial. So for example, here's a line, here's a couple of points. There's A, which is the point -3. There's B, which is the point -1. C is, well, a point with rational coordinates, say 2/3, between 0 and 1. D is the point 2, and E here is the point, say, 8/3, between 2 and 3. Okay, so let's have a look at some vectors. How about the vector between A and B, the displacement vector between A and B? So we write it as AB with an arrow on top, meaning we're starting at A and we're finishing at B. And how do we write that thing down? Well, it's going to have round brackets, and what's inside the round bracket has to be the difference between the B coordinate and the A coordinate. Okay, the B coordinate is -1. The A coordinate is -3. So if we take -1 minus -3, we get 2. So that's what sits inside here, that's 2. That corresponds with our intuition. Geometrically, we can see that going from here to here, we have to go over 2. 2 in the positive direction because we're moving right. And this is the positive direction in the x-axis. Now have a look at CE, the displacement vector between those two. There's C, there's E. To get the vector here, we have to take the difference. We have to take 8/3 minus 2/3. Well, that's 6/3, or 2. So the vector CE is also equal to the vector 2. So this displacement vector equals this displacement vector, even though they are in different positions. We'd have to translate this one to get that one, but they're actually the same vectors. And what about, say, the vector U, which is dB? Okay, starting with D and then going to B. Well, what we have to do is we have to take the final entry, which is the B, which is -1, and subtract the initial entry, which is that of D, which is 2. So -1 minus 2 gives us -3 inside. So the vector dB is the vector with a single component -3, representing the fact that this is going to the left on our oriented axis. So vectors can have positive entries, can have negative entries, could also have 0 entry. If it had 0 entry, then it wouldn't be going anywhere. That would be a vector like CC, starting at C, ending at C. That would be the 0 vector. It would be represented by round brackets with a 0 inside. So relatively simple vectors along the one-dimensional line representing displacements between points, and obtained by just taking the difference between the coordinates of the points involved. Final minus initial. Okay, so now let's look at two-dimensional displacement vectors. So suppose that we have 2 points in the plane, A, which is say AB, and B, which is CD. So these are affine points. Then the displacement vector V, written as AB, the vector AB, is defined in the following way. This is how we define the vector AB. It's the vector whose components are C minus A and D minus B. So the difference between the x coordinates, the difference between the y coordinates. That's the definition of the displacement vector. And it is a vector because it's in round brackets and it's got a pair of entries. So for example, if we have a couple of points in the plane, say A is 1, 1, B is 4, 2, C is minus 1, 2, D is 2, 3, then the vector V, which is the vector AB, how do we get that? We just look here. We look at the difference between the x coordinates, so 4 minus 1, and the difference between the y coordinates, 2 minus 1, we get 3, 1. And that's the same as the displacement vector CD, because if we compute that, the difference between the x coordinates is 2 minus 1, that's 3, and 3 minus 2 is also 1. So this vector AB is the vector V. We can put a V there. And that's also equal to CD. They're both equal to V. So let's actually write that down. So we could give that the name V. And this is also the vector V. So vectors in the plane can manifest themselves in lots of different ways. Basically, we can take a vector like this and translate it wherever we want. As long as we don't move its orientation or change its extent, it's going to be the same vector. And here's another one. U is, say, AC. That's going from here to here. Let's give that a name. Here's the vector U. Then, how do we calculate that? So it's going from A to C. So we take the C point and the A point and take the difference. Minus 1 is minus 2. And 2 minus 1 is 1. So the vector AC is minus 2, 1. And notice that, this is just very natural. Going from A to B, you have to go over 3 in the x direction and up 1 in the y direction. So that's the vector 3, 1. To go from A to C, you have to go backwards in the x direction by 2. In other words, you have to go minus 2. And then you have to go 1 up in the y direction. So these displacement vectors really are measuring the separation between 2 points, telling us how far we have to go in either of the coordinate directions to get from one point to another. A fascinating aspect of vectors is that they naturally have an arithmetical structure. This is something that points don't have. Points don't have arithmetical structure particularly, but vectors do. Somehow being differences of things makes it easier to combine them. So in the one-dimensional case, here is how that arithmetic begins. It begins by defining the sum, the difference of vectors, and also a multiple of a vector. So here in the one-dimensional case, we have 2 vectors, A and B, and to add them, the definition is we just take the vector A plus B. Here we have the difference. A minus B is the vector A minus B. And here what we're doing is we're multiplying the vector A by some number lambda. So lambda is just some arbitrary number, meaning rational number. And so lambda times that vector is by definition the vector lambda times A. Correspondingly, in the two-dimensional case, it's very similar. We can define the sum of 2 vectors, the difference of 2 vectors, and a multiple of a vector in an obvious way. So to take the sum, we just take the sum of the x coordinates and the sum of the y coordinates. To take the difference, we take the difference in the x coordinates and the difference in the y coordinates. And to multiply the vector by lambda, we just multiply each of the entries by lambda. So these operations, sometimes called addition or perhaps vector addition. Here's subtraction or vector subtraction. And here's scalar multiplication. to remind us that we're multiplying a vector by a scalar or a number. So note that multiplication of vectors is not defined. We do not define the product of two vectors. Later on, one does, but not in perhaps an obvious way. So these are arithmetically defined operations, but of course they do have a geometrical meaning. Otherwise, they'd be rather pointless. Very important geometrical meaning. The geometrical significance of vector addition and vector subtraction is illustrated in this example. Here we have the vector u equals -1, 3, going from there to there, and the vector v equals 4, 2, going from here to here. Notice that we've arranged that these two vectors are not just anywhere, but that they happen to be both emanating from the origin. What's actually really important is that they're both emanating from the same place. That makes describing their sum and their difference much simpler. Remember that the vector, say v, vector 4, 2, can be translated and still the vector 4, 2. So we could go from here to here. That would still be the vector 4, 2. We could translate it in many number of places. So if we put it right here, that's a particularly convenient spot because it's emanating from the origin. All right, in that case, we see here in this diagram a parallelogram. Okay, so here there's a vector v and here's the vector u, and the other sides are parallel to these sides. Parallel. So again, we're using this parallelism, which we're assuming that we have around in this affine geometry, to create this parallelogram. So this is actually a copy of the vector v. And this is actually a copy of the vector u. This vector and this vector are exactly the same. So when we look at u plus v, what we're doing is we're adding the x coordinates to get 3. We're adding the y coordinates to get 5. We get the vector 3, 5. Where is this on our diagram? Well, 3 over in this direction, 5 up. It's the vector going from here to here. So this green vector is the vector u plus v. There it is right there. So that's a nice geometrical significance to the sum of two vectors. It's the vector that goes along the diagonal of the parallelogram that's spanned by u and v. And another way of thinking about that is it's what you get when you take v and then you combine it with u. So you go along here in the direction v, and then starting here you go along the parallel translate of u from here to here. So the combination is to go from here to here in 2 steps. Step 1, step 2. How about u minus v? That's a little bit more subtle. So the vector u minus v, it's the difference. So -1 minus 4, that's -5. 3 minus 2 is 1. Where is this thing on the diagram? Well, it's also on the diagram. It's the other diagonal of this parallelogram. It's the red vector. Well, you can see that because to go from here to here, we have to go 5 over in the x direction and 1 up in the y direction. So this is the vector -5, 1. So we can write u minus v under the red one. That's where it is. And so what's the rule? The rule is that if we've got the vector u and we've got the vector v, then the vector u minus v goes from the head or the final part of v to the final part of u. So u minus v, we're going from the final part of v to the final part of u, to the head, from the head of v to the head of u. And maybe one way of remembering that is in terms of sums. If we take the vector v and we add u minus v to it, then it makes sense that we get the vector u. So that's another way of remembering it. The vector v plus the vector u minus v gives us the combination total of u. So the sum and the difference of two vectors are found geometrically in terms of the diagonal vectors of the parallelogram formed by u and v. That's a very nice and important geometrical interpretation of the sum and the difference of two vectors.